Alright, so troubleshooting. We need to be able to configure static routes and work out if they're working correctly. So we need to understand the process that we go through to forward packets, and then look at some of the common issues derived when we use static routes. So an entry in the routing table is identified when a packet arrives, and it needs to work out what to do with it. So it looks for an entry in the routing table that is the longest match. So it looks for the destination network address. If it doesn't find one, it will use the default static route if it's configured. If there's no default static route and there's been no match, it drops the packet. Fairly straightforward general advice on forwarding. So if we get a match, the packet from PC1 arrived in router 1, and it is then forwarded out of the serial interface on its merry way to router 2. Router 2 receives that same packet on its interface. It de-encapsulates it so that it can process based on the layer 3 information, and does the same lookup to find out what to do with the packet. As this is going to PC3, it will re-encapsulate it and send it out the serial interface that connects to router 3. Router 3 receives it on the serial interface from router 2, goes through the same process, determines it has to send it out the local Ethernet interface, and before it can send it on its way, it has to do a match between the layer 2 and layer 3 addresses, so it looks up its MAC address table. If there's no layer 2 address in that table for that specific destination IP address, it sends an ARP request out, gets a reply, and then encapsulates the packet and sends it along its way. PC3 will then receive it, pick it up, and process it as normal. So that was normal behavior of traffic transference. So what could go wrong with using static routes? Well, any particular interface can fail for a number of reasons. If it's connected to the outside world, the service provider could actually drop the connection. The links in question could become congested, overused, so we can't send traffic down it. The buffers fill up and we drop packets. Lastly, us as administrators are only human and we can make mistakes. Well, You can. I'm God, I never make mistakes. Oh, as a teacher, that's the excuse that I always use. And what was the other excuse I use? I did it deliberately to see if you were paying attention. We're human. We make mistakes. It's that simple. Whether it's via typo or misreading the information, it doesn't really matter. Occasionally, we make mistakes. So, as the local network administrator, we need to analyze what is going wrong and find the point that is the source of the fault and resolve the issue. So hopefully by now you've worked out that troubleshooting revolves around 6 steps, which we've always gone through when troubleshooting. But when we're talking connectivity, we use the usual suspects: our ping, our trace route, show commands to find out what's going on. So our ping tells us whether or not we can get to our destination. If we can't get to our destination, you use the trace route command to find out how far in our path we get until it fails. This helps us pinpoint where the fault is. Using our 3-router example from last chapter, sending traffic from router 1, if it only gets to router 2 but doesn't get to router 3, we know that there is an issue between router 2 and router 3, and we can go to router 2 and start diagnosing what's going on at the potential source. Why would we check the routing table? To verify that the actual network is listed so that we can forward traffic to that network. Whether that's an explicit entry of the remote network or a default, it still needs to be in there. Show IP interfaces will give us information on how our interface is behaving. So one of the things we want to check is to make sure the interface is up and and it's configured correctly and talking to our neighbors. Show CDP neighbors will allow us to get valid information about our links to our neighbors if we're using Cisco devices. LLDP is the generic command that we use in non-Cisco environments. But that command or protocol, the LLDP protocol, is not running by default on Cisco devices. So as all of our devices are Cisco, we use the show CDP neighbors command. So first thing we need to do if we have problems getting from PC1 to PC3 is check to make sure where the fault runs. So from router 1, we check the interfaces along the path. This tells us whether or not we can get to the destination. So the first one, pinging from router 1 to router 2, successful. Router 1 to router 3, successful. That tells us that the device itself can get there. Now, if we could ping from router 1 to router 2 to router 3, but couldn't get to PC3, I would then look at router 3. If I was unsuccessful in my ping between router 2 and router 3, I would then go to router 2 and look deeper at the connection between those two devices. So I'll just modify this little slide here. And say unsuccessful. Now is unsuccessful one way we could hyphenate it. For the ease of this PowerPoint, we'll just put it as one. So that way it moves on. Okay. So in this scenario, we would then go to router 2 and look at our route, because our connection to router 2 was successful, our connection to router 3 wasn't. So we now look at router 2 as a point of failure. Using the show IP route command, we notice the connection is in there, pointing to the wrong address. So this tells us that something went wrong. Now, what went wrong, and the other scenario would have worked, but generally speaking, you wouldn't get a response back. And this is why this scenario isn't the best way of doing it. Because when we generate the ping command from router 1, our source address is at the outbound interface, which is 172.16.2.0. So router 2 would always respond because it's a directly connected network. It knows how to get the traffic back to it. So when we send our initial ping request to router 2, it knows how to get back. When we send it to 3, it knows how to get it back. So that's the scenario that was originally there. Now, if you have an issue between PC1 and PC3, you would be doing your initial ping sweeps from PC1. So you would ping from PC1 to router 2. And then you would have discovered it couldn't come back. Okay, you don't abandon your original source until you find out where it stops. I wouldn't have left PC1 and logged into router 1. Alright, because my connectivity issue is from PC1. So the first thing I'm going to be checking is whether I can get to router 1, gateway, router 2, router 3. Alright, I wouldn't have left PC1 and gone to router 1. So, flawed troubleshooting. But, alright, if we ignore their flawed troubleshooting and go back to router 1 scenario, it works. So, if I can get to router 2 and router 3 from router 1, there's no reason I would assume there's a problem with the router 2. Alright? See where the logic of this falls apart. Only by maintaining our original source of what the failure is. So we're troubleshooting why PC1 can't get to PC3. So you eliminate the connectivity issues from the source. You check the gateway. You then check the next link. It would fail because router 2 says I have to send it to 192.168.1.1. So it would send my reply to router 3. I would know now that I need to go to router 2 because I'm not getting any replies to my ping commands from PC1. I wouldn't have gone to router 1. I then would look at router 2 and find out what my issue is. I would have then discovered the static route was misconfigured and pointed to the wrong next hop for 172.16.3.0. So my replies were going to router 3. By changing the static route, I then pointed back to router 1, and then I would have full connectivity back to PC3. So you just need to follow a logical troubleshooting exercise. Don't go jumping off onto other devices without following and troubleshooting from the source. Okay? Why jump from PC1 to router 1 if you couldn't confirm you had connectivity from PC1 to router 1? Okay? Chalk it up to a very bad scenario for troubleshooting on that slide. There's a couple of packet tracer activities for you to get your head around some troubleshooting. So what we went through was a reminder of how packets are processed through devices. They're picked up on one interface, de-encapsulated, so the frame headers are removed. It then looks at the destination network in the IP header, checks its routing table. If that network exists in the routing table, it then can forward that packet to the destination by re-encapsulating it as it puts it on to the cable connecting to the next hop. This process is repeated until it gets to the final router, where it doesn't send it to another hop, it's sending it to its final destination. So it does a lookup in its MAC address table, does an ARP resolution if required, and then encapsulates it with the final destination's information. Along that process, if at any time there is no explicit match of any route or default route, it's discarded. And there's the rest of the text for what I said on the first slide. That's the downside of me just talking and not reading the slides off to you. Occasionally I get in front of the text on the slides. That's a good thing. Now, as a reminder, the core commands we use for troubleshooting are ping, traceroute, show IP route, show IP interface brief, and show CDP neighbors. Now, these are the commands that form our key. Now, if we're doing a traceroute from the PC, which would have been a valid option if we couldn't ping to PC3 and couldn't work out where our ping failed, that would have shown the trace going through router 1 and terminating at router 2. The command is different on a PC depending on the operating system in play. Trace RT is Windows version, so just remember that one. And that brings us to the conclusion of chapter 16 and the conclusion of the theory for the SRWE course. So, good news.